Okay, welcome everyone to the Ask CT Contributors webinar, 5 Tips to Avoid Tap Breakage. I am Dennis Spaeth, the publisher, editor, and owner of Cutting Tool Engineering. And we're here today, today's webinar, to reinforce our March Cutting Tool Engineering article on boosting threading efficiency, which was contributed by Mugi Franken USA, a company with a long history in tapping technology. Industry veteran Tom Kowalski, a regional manager for Mugi Franken USA, will draw upon his 24 years of technical expertise with the company to share 5 tips that will help you avoid tap breakage. Welcome, Tom.
Thank you, Dennis, for having me. My honor.
Sure. Well, our March article covered how to improve the threading efficiency by utilizing the knowledge of application specialists. Today's webinar will delve into the intricacies of tap selection, drilling considerations, and crucial decision-making that Mugi uses for optimizing thread quality and tool life, and avoiding the dreaded broken tap. The discussion today will include a little tapping history to remind us of just how much we should appreciate modern machine tap and its development. We also will learn about the importance of drill size selection for machine taps, the Mugi Franken tap selection process, how tap holders work to improve the tapping cycle, lubrication for taps, and the speeds at which taps can be operated. To start, Tom, can you please just share some history about a Mugi and tapping?
Sure, I'd love to. Dennis, Mugi Franken started in 1920. Gentleman named Richard Glimpel started this company, and in a very short amount of years from its beginnings, he introduced and perfected, patented the world's first single finishing machine tap with spiral point. And that set the company Mugi Franken on a course. So over a century, Mugi has been manufacturing, innovating, inventing, perfecting, cutting taps, forming taps, tap holders, workpiece clamping. With our Franken division, it's milling, end mills, and also today we also offer solid carbide drills to help us better have great performance with tapping products. So it's a very rich history. I'm going to also kind of put this as my origin story as well, if you'll allow me.
Yeah, tell us about your experience with tapping, because I know this is good.
So we're looking here at a picture of the Philadelphia Naval Shipyard. And I figured this morning, it was about 33 years ago, I was a mechanical engineering student at Spring Garden College in Philadelphia. I was given the opportunity to co-op at the shipyard. That led to a full-blown apprenticeship in the machine shops, Shop 31 at the shipyard in the early 1990s. And I had a great experience there, got to see a lot of cool stuff. But it also leads me to tell you my origin story with tapping. In Philadelphia in the summer, very hot and humid, the shops at the Navy Yard were not air conditioned. And my first experience tapping was with hand tapping, obviously. And it was hundreds of parts, and it was very, very tough work. And it gave me what I would tell you today, and what I wanted to try to reiterate with our crowd today, is to have an appreciation of how far we've come. And the company Mugi is really a big part of how machine taps today are so automatic and maybe overlooked. So just a little reminder that most all tapping throughout history has been done as a hand tapping, a very manual operation where you have to have good work support. You got to have a very clean working area, right? And what we're doing with taps, if you're not aware, a set of toolmakers taps were always used to develop the thread profile in steps. And in the case of a toolmaker set, it's usually 3 taps, could be 4, but it's a rougher and then a semi-roughing tap and then a finishing tap. And I got to witness this toughness firsthand by doing this manually. And really, it was Richard Glimpel's designs and his innovation that made the machine tap that we use today really one tool that replaced 3 tools. So it's important that we appreciate and have an understanding, if anything else today, of really the magic of a machine tap today and how it has replaced hand tapping.
That's good.
So another point that I was going to touch on is I wanted to give a shout out to all my colleagues in the field. Amugi, Franken, USA, and in Canada, we have an extensive team of product application specialists that are in your area to lend a helping hand, to come to your shop and listen, to troubleshoot problems, and to really make sure that you get the best performance out of our tools. And tapping obviously is a big thing that we do because, again, our conversation today is really all centered on how do we make plans, have a plan to avoid tap breakage and smile more.
Smiling is good.
So what I was going to do is go back to just to reiterate that for a long history, right, machine tapping is really an automatic, a magical event that happens in seconds. And what we're going to do is go down through some of the things I think are real easy precautionary things you can do in the machine shop to make machine tapping more reliable and to avoid tap breakage.
Peanut butter and jelly.
So really, we're gonna start by talking about drills because drills kind of set the stage. They can make or break our tapping, and drills and taps are really linked together like peanut butter and jelly. And for machine tapping, what we always want to talk about is having really larger drill sizes for machine tapping. So know that every thread, you have a range, you have a min and you have a maximum. And with today's carbide drills, mostly carbide drills we're talking about, we have a chance and an opportunity to make a very precise bore. That's going to create our minor diameter. We're always operating with a specific range. And we are always going to try to use larger, slightly larger drill size diameters for machine tapping. And when we talk about what that sets up, it's really the percentage of thread, the thread profile. So one of the observations I've made over the years is a lot of times with breakage and having poor tap life and very difficult materials is a lot of times when you walk into a machine shop, you're referencing very old drill charts that historically were set up with 75% full thread for hand tapping. Because again, all throughout time and again, the tapping operation was a hand tapping operation, and that's really where 75% full thread comes from. Today, with modern machine tapping, right, and carbide drills, we can always get you to the best pre-tapped drill size so that the machine tap will operate in a much better light. And this would be about a 65 to 70% of the thread profile. And this is plenty for any kind of tapping operation. So think about larger sizes always when you're doing CNC machine tapping. Think about larger drill sizes when we are dr- tapping deeper threads that sometimes can be 3 times D, 3 times the nominal thread diameter and depth. And also think about larger drill sizes, right, for stronger materials. Stronger materials being things like in aerospace industry or in the medical field.
Okay. So, do you want to get into talking about the Amugi tap selection process and 5 key questions for that, when properly answered, will lead to the correct application machine tap? Uh,
Sure. We at Amugi have a very extensive program of cutting taps, forming taps, now thread milling tools. Um, and really for us to go down this path to get you to the best option, there's these 5 points of information that we have to process with you to get to the right place where we want to be. And they are as follows. The first and most foremost thing is we want to know what the workpiece material is that you're working with. And really the second part of this is to know what that workpiece material condition is, what the hardness is, what the tensile strength is, and so on. And that's really going to pinpoint for us how to start the conversation of where to get to the right cutting tap or forming tap. The third thing we need to know, and especially this is important for cutting taps, is the type of hole. And we're going to talk about why that's important. 4 would be the thread depth, because a lot of times there are going to be physical limitations on how deep a machine tap can actually cut or form the thread. And the last thing, ironically, is usually the first thing that people tell us. But really, after we get through those 4 points, the last thing we are looking at is the thread size and the tolerance of the thread. So let me just go point by point and explain why these are important to us. Now, all this is set up in a way because, again, like I said, our catalog system, it stores these tools for us to use with you. It's over 600 pages. It's very comprehensive. And really, this question, these 5 points of information are needed to guide us and navigate our system of storage. So let's talk again about the first 2 points because they're really going to complete the workpiece material, not only the type, right? And we use this identification chart, which you should all be familiar with, that's used with carbide tooling, with insert tooling. We use the same ISO P, M, K, N, S, and H system. And then also point 2 is the condition of your material, because again, we need to know the hardness or the tensile strength, because even within a similar material, there are different heat numbers and so forth, which are going to really drive us towards a choice for the best starting point for your tool, your tap. Now, the reason that workpiece material is really so important is understand that with machine taps, the cutting geometry is defined by the material that we're going to work in. And the 2 things that I point out here, the rake angle, this is where the chip is formed and rolled in the flutes, right? So it's very important that we have this workpiece material type. And then the other thing that is governed here is the profile relief. And this is how the machine tap, again, goes through its cycle in seconds. So it's how it flows and cuts through the material. And these are very important features that you don't see, but they are different as we go through the different geometry families. And what I have shown here is just some of the nomenclature in the Amugi system for our different cutting geometries. The same holds true if we're talking about cold forming taps. Now, cold forming taps are not creating chips, but again, they are forming the material or pressing the material into a thread. So again, for the same reasons, we have the type of shapes that the polygons and the number of forming lobes that are used to press the material into your thread form. And all modern cold forming taps have some type of coating, which is like a first level of lubrication. So again, workpiece material is actually governing the designs of the cutting and forming taps. Okay, and that's when we can talk about different families of cutting or forming taps as being material specific. They address certain, in the case of titanium, very elastic materials, right? In the case of nickel, very strong materials, and stainless steel, where again, we have to have very positive or high cutting geometry. The third point is something very unique to taps, and we all should understand that cutting taps, we have to know the whole type because the chips that we're making in the tapping process, they have to be just like in the hand tapping option, they have to be removed and out of the way of the working surface. So in the case of through holes, we can simply use that spiral pointed tap, right, to push the chips out of the way. But in the case of blind holes, we have to have spiral flute type taps that are augering or lifting the chips out of the hole. So this is why this is so important that we know the type of hole, because in the tapping, the chips must be transported. Number 4 is thread depth. And I put up this picture and with a little bit of an explanation. Everyone wants their threads deeper and deeper, but you got to understand there are limitations. So this example, we're just showing a 3/4 10 tap, if you will, spiral flute for a blind hole. And if you wanted to have 1.5 inches, which is not out of the ordinary, 2 times the nominal diameter of thread depth, that would be 15 turns, right? If you took the circumference of each turn times the 15, you'd have 35 inches of chip swath in each flute. But you have to also remember you have 4 flutes at 35 inches, and you had 3 cutting teeth, or the lead is 2 to 3 threads. So there's separate springs being made on every cutting tooth. That would equate to over 400 inches of swath being made, and that has to be eliminated or augured out of the blind hole. So you can see why thread depth is very important for us to consider when we talk about automatic machine tapping. The other reason that it's important, though, is in blind holes. We always ask, what's your maximum drill depth versus the minimum full thread depth? Because remember, the machine tap combines 3 different taps into one tap, and all that is condensed into the cutting chamfer or lead of the tap. So the tighter you want to go to the bottom, we need to know sometimes if it's less than 2 threads, we have to think about thread milling, because a machine tap physically has to have at least 2 thread leads to develop that thread profile as one tool. So for blind holes, number 4 is very important. We need to know the thread depth. And in the case of that depth, we also need to know what's the difference between the maximum drilling depth and the minimum full thread depth that you must have. And that leads to this explanation about chamfers or leads on cutting taps, right? And this is a DIN listing. Our spiral point tap would always follow the Form B, which would be 3.5 to 5.5 leads to develop the thread profile, and that single finishing tap. For blind holes, it becomes a little more condensed. Typically, we try to use modified bottoming, which is Form C, and that's 2 to 3 threads. It takes us 2 to 3 revolutions to develop a complete thread profile, right, with the machine tap.
Yeah.
And then the worst case scenario for us is the Form E, and Form E is 1.5 to 2 revolutions. So you can see that, again, with machine taps, we're doing all this work in a very short area, and you have to make some decisions about larger drills and things like this to have success. Now, the last point, and like we said, it's usually ironically the first thing we hear on the phone, but it's the thread size and tolerance. And at Amugi, you'll see that all of our taps, whether it's unified threads, metric threads, will be marked with the thread size. In the case of the unified series, the thread size and the pitch, and the series, obviously, and then the class of fit. And usually that's 2B or 3B. For metric, it's usually 6H, could be 4H, different oversize that we stock. But we do not mark Amugi taps with H and D limits. And this next slide, I just illustrate the difference between the go and the no go. All machine taps are oversized, right? And they're within the range of the standard gauge. So obviously, forming taps are up at the very top of the tolerance, right? Because they're pressing the thread. And then cutting taps can be really in the 30 percentile to 40 percentile because, again, they're cutting some clearance. And this just illustrates that we are making application type taps, which sometimes will take liberties. We also control the tolerance of our taps at a very, very small tolerance in house. So, again, I just wanted to put that up for you guys to see.
Cool. You know, can you talk about the role tool holders play and, just how machinists could select the best tool holder for their tapping applications?
Sure. You know, at Amugi, we've always made taps and tap holders together. We are the only tap company that makes a full complete line of tap holders. Tap holders are so essential for tap performance. Um, for numerous reasons. But one of the things today, even though most CNC machines have synchronous spindles, people often ask, "Do I really need to have a tap holder?" And I would tell you yes. And we'll try to show why having the right tap holder will make all your tapping applications as far as machining go better. So I'm going to advance just again, some of the unique things that we're trying to point out about tapping, machine taps. I put up this slide, which, is showing a cut tap cycle. And you could break that cycle, which literally could be 5 seconds long in a CNC machine. There's seven different stages of that cycle, right? But the thing that is very unique for taps is in yellow. You must remember that taps are the only tool in your magazine that accelerate to such a speed. They come to a complete stop in the middle of the cycle, and then they reverse direction and come back out of the hole. And that difference of direction, forces, making chips, squashing chips, all this stuff we don't think about, but stop for a second. Freeze this in your mind. There's a lot of complications here. And this is why tap holders are so important. You have to have an appreciation of what the machine tap is doing. Like we said, it's replacing 3 hand taps, right? It's squashing all the work into that lead, right? Which we said more and more people want to have full bottoming. And then the other thing that taps have to do, along with getting rid of your chips, out of a blind hole, it's much more difficult. Out of a through hole, it's all pushed ahead. But again, it's a lot of work. And then this change in direction. So I would tell you, one of the most important things is to really think about how you're holding your taps. Even in today's machines, we're going to show you why that's important. So taps, again, they're sharpened screws. When they rotate, they move. A spiral flute tap with a high positive rake angle and profile relief is going to flow very freely. You can feel this on a Bridgeport machine if you ever try this. I'm going to show you, some tap holders I have with me. And these are tap holders that have what we call a compensation feature. If I hit the bottom of the hole, I need a compression uh, allowance. If I'm using a tap with a spiral flute, I might want to stay and just let the tap guide itself. So there's a tension compensation feature. And for older machines, this was the way taps could operate and cut very nice, precise threads. If it's a spiral point tap like this one, as it dulls, it's going to increase the amount of force, okay, that it pushes. So we have a hard start feature on this tap holder that prevents, again, from oversize. I'm going to ask that we go back to the screen because, again, like I said, spiral flute taps will always feed rapidly, and we need maybe some tension to hold them back. So think about a team of horses, and we have to sometimes hold them back. In the case of spiral point, it's the opposite. As the tap wears, we're pushing against the tap. So we have that hard start feature that I was just showing you. So this was how tapping was done, even as an automatic cycle in drill presses and older machines. So I just, again, tap holders are important, and how do we get to the right type of tap holder? And just like when we decide where we're going to start with tap choices, our tap holder choices have to do with first, and the most obvious thing is the type of machine tool we're using. Today, most machine tool choices are CNC machines that have synchronous spindles, right? But again, there's different machines that we have to think about, different choices. The second thing that's important is, and that picture there kind of illustrates this point, but is the tap size. A Mugi has experiencing making very large cutting taps, up to 130, 160 millimeter cut taps. You see a picture there with a tap driver and robust tap, just to illustrate that point. So tap size. When we get to very tiny taps, again, we have to make different choices. Maybe we need to have ER collets that lock the taps with no movement, because again, these are little toothpicks, if you will, running at very high speeds in your CNC machine. And then the last thing is the tapping speed. Obviously, we're going to show some things at the end here where we can go faster than your machine is even able. Okay, and we'll talk about something called speed synchro. So, feed types. Like I said, most of our choices today have to do with CNC. I'm going to show a typical example again. This is a soft synchro. This happens to be a coolant fed tap. So we are sealing all the coolant and blowing it out the bottom of this tap. So we use ER collets. Okay, and with ER collets, I'm just going to show you real quick if I can grab one here. ER collets for taps would always fully encapsulate the tang, the square on the tap shank. Why? Taps reverse. Remember, we made that point? One of the only tools in the middle of its cycle that has to reverse direction. So we're creating chips, right? And a lot of torque on the way in. And then we come to a complete stop and we reverse the tap, squash chip roots, and clear out debris as we're coming out. So we have to have collets that have fully encapsulating the tang of the tap shank. We can go back to our slides. So we'll talk about soft synchro. Really, that's the best way for synchronous. When we go to older machines, maybe large boring mills or drill presses, they still might have NC controls, but they don't have a fully synchronized spindle where the rotation and the feed axis are talking to each other. So in that case, we use tap holders that have tension, right, and compression that give us an allowance for that error that could occur. And then finally, in manual machines, you have to have some kind of compensation, and that could be a tension and compression holder. So, soft synchro, I am a big fan of soft synchro. Soft synchro technology was invented by Amugi in the mid 1990s, really at the first introduction of rigid or synchronous tapping, where an encoder is on your spindle. But even with that encoder, there's always going to be our Amugi, because we know taps. Our engineers came up with the concept of soft synchro. Now, what that means is in a soft synchro holder, the compensation that we're using is minimal. So it's a minimal compensating holder. We're talking about 20 thousandths of tension and 20 thousandths of compression. And I'm going to use my pointer. Hopefully you can see this, but there's elastic washers, right, that are separating the spindle from the tap. And 90 degrees to that are two grooves with ball bearings in them. And what we're doing is we're allowing the tap to float minimally. But what this graph is showing you at 2000 RPMs, right? This tap in a solid tool holder has a tremendous amount of axial forces that are just pushing and pulling on it. And obviously, the spike here is the spindle reversal. The same tapping cycle with the soft synchro technology as the, if you will, like the cushion between the spindle and the tap, it takes about 70% of that axial force, that unneeded force, off the tap every threaded hole. So it's just a smart idea. It's the best way, I think, I say, to go to war. And that's what you're kind of doing when you're going into these tapping cycles in very difficult material. Soft synchro gives you the best bet for your tap. It takes all that wear and tear off of every cycle.
Yeah, can you provide some insight about how lubrication and operating parameters can help enhance tap performance and longevity, especially with machining environments, high-speed machining environments, and challenging materials?
Sure, Dennis. We tried to point out today, or at least I try to illustrate some of the uniqueness of taps. And one of the things about taps that you should always think about lubrication as the key for tapping. It's one of the most important things for modern taps to operate. If you look at a CNC machine, you have usually emulsion coolants today with lights out type machining. You don't have a lot of cycle stop time to have high, straight oil or lubricants like that added to the process. So, but taps really do require a high quality, a high degree of lubrication. And the reason is, again, they run at relatively lower speeds. There's a lot of surface contact. They make an enormous amount of chips in the case of cutting taps. And forming taps, they create a tremendous amount of heat because of the pressing, the forcing of the material to flow into a thread form. And in water soluble coolant environments, they have to have the oil, so for me, I'm always asking people to look at their coolant concentration in this modern CNC machine. We like to see like a 10 to 12% emulsion for tapping. This is always maybe a little more than what people want to give us, but when they do a lot of tapping, they'll usually see it our way. This graph that I'm showing here has been with us a long time, but it illustrates the torque, okay, that a tap here, fully dry, you can see the top line. The tap is generating a tremendous amount of torque, not only in, but then out. And then there's two levels there. I think it's blue and green if my color is
You're
true.
right.
And they are really minimum quantity lubrication added to the tap cycle and measuring the torque. The bottom is conventional coolant in the sump, about 8%. And again, you can see it's a 4-to-1 difference in reducing torque in the tapping cycle. And torque is wear, torque is heat, right? Torque is really the measure for us for tool life. If we talk about what is a good tapping fluid, I have here an Amugi tapping fluid bottle. And some of the things that we put on there, cuts precise threads. Yes, that'll help. Reduces tap breakage. Yes, it will. Slows tap dulling, of course. Um, but the things about this fluid that make it kind of unique is it doesn't burn or evaporate. It's a lubricant. It's on a microscopic level. It's like liquid ball bearings. And this is going to drastically reduce, in the case of a cutting or a forming tap, the amount of torque. Okay. And that is what all good tap fluids do. They don't burn or evaporate. You shouldn't see a lot of smoke. Um, you could put them right on the tap. You could still run your coolant and it's not going to wash away. You'll probably do your bolt circle or whatever you're doing with one application, and it effectively lubricates the tap where it needs to be at the working surface, and it's going to really increase your chances of having success with taps. And it could be our fluid, it could be a number of other fluids, but it has to be a really high quality lubricant that doesn't burn or evaporate. So I'm going to show you one of our company lab reports where we did testing in very tough material tool locks. And this is just showing you all the points that we're talking about with getting tap geometries, comparing the differences. We have in here a mention of coolant. E is emulsion, O is for oil, P is for paste, like a solid. In the most extreme cases, we have to use sometimes like a solid lubricant, but oil would be like the Samugi, and emulsion is what, again, for lights out type operations. But this really shows you coatings are another part of lubrication today for modern machine taps.
Yeah. Can you talk about how speeds and feeds factor in?
Sure. So probably our final, we kind of went through a journey, talking about all kinds of different factors, and it led us really to this final discussion about tapping speeds and feeds. Let me eliminate the feed question, right? Feeds, we defined the feed of the tap when we made it for you and we ground it. And that is every tap pitch is your feed rate, right? So um, that is for each revolution, the tap advances by its pitch. So whatever we end up with the speed, you're going to determine the feed rate because of its pitch. So it's really part of its DNA when we made the tool. So let's talk about tap speeds. Tap speeds range in our book. I believe it was from 3 to 262 surface feet per minute. So good luck. It's a pretty wide range. But let me give you some background again. Just like choosing the tools, just like choosing the right tap holder system, right? Speed is really defined by the workpiece material, right? That range of 3 to 262 is wide open. So I was going to give you the Tom Kowalski 5 second, nickel. There's three numbers you should always keep in mind with taps. For me, it's always worked out this way, and it's 15, 30, and 60. And let me explain what those numbers mean to me. When the material is very, very tough, right, like titanium alloys, nickel alloys, very tough stainless, 15 surface feet is a good place to start. It's an excellent place to start. Okay. When we talk about normal materials for machine tapping, like steel alloys, 4140s, 1018s, the bread and butter materials, 30 is where that number 30 comes in. 30 SFM is a good place. It's a safe place for us to start. And then the last one is when we talk about softer materials, materials that maybe in their own right could present problems, but they are softer than most, like aluminum, like brass. Materials like this that are very easily cut or very easily formed. 60. 60 is a good place to start. 60 surface feet. So those three numbers, 15, 30, and 60. If anything else, that's a good starting point. And then the other thing that's going to govern tap speed is the machine tool. Obviously, most modern machine tools, the limiting factor really is inertia. Because why? Taps have to stop in the middle of their cycle and reverse, and that's a collision in the workpiece, right? And it has to be done with finesse. We talked about our soft synchros, right? The soft synchro here is a cold forming tap. We have a coolant flush disc inserted into the nut. We can put a beautiful stream of coolant along the cold forming tap, and we can really, on a Cat 40 size spindle, we could be tapping up to 2,500 RPM. Maybe if we go north of that, we could program that, but we probably won't realize all that in reality because of that stop and reversal. Larger taps, we have quick change tooling, and there's a little bit of play. So maybe we have to slow things down for that type of tap holding system and that size of tap. So we go back to this slide, and we're really looking at the last and final point. But again, we said how important, how crucial lubrication is for taps. It's really we have to get that right. That lubrication is so important, and how that coolant in many cases is delivered. If it's through the tap, great. Smaller taps, we can't do that. So hopefully we can use a flush disc or something to get high pressure coolant around the tap. But remember, the tap has to be part of the workpiece at some point, and it's encapsulated in the material. So that's going to really govern how fast we can go. But I think if you start out with that 15, 30, and 60, you'll always have a good starting point with the toughest, the normal, and the soft materials. Now, one of the things that Amugi has innovated and invented is called Speed Synchro. We're going to show you a video of Speed Synchro because Speed Synchro came about. Speed Synchro came about because, again, taps have to stop and reverse, and machines, to effectively do this at very high RPM, are not going to be able to do it to a certain extent. So what Speed Synchro does is it takes the input rotation, say, of 1,000 RPM at the spindle, and it puts it to 4412 at the tap. And that is because of the gear. It's a speeder head, but it also has soft synchro technology built into the speeder head. So again, you're going to see a side-by-side rigid tapping, stopping at 6,000 RPM, and also the same tapping cycle at nearly 12,000 RPM. But again, the machine only has to get to a quarter of that rotation. This saves a lot of energy, a lot of wear and tear. It makes for better tapping cycles, and it really literally is the fastest that you could physically tap in a machine. And we can also monitor all the operation data with our smartphones today just by holding it up to the side and having the data come to our phone. So Dennis, that's really the latest technology in machine tapping, that right there.
Yeah, Tom, I just want to ask a question. I think that's come in from the audience. So what if you can't use any sort of fluid at all? And yeah, take a sip.
Thank you. Well, if you can't use any kind of lubrication fluid at all, we're going to have sleepless nights because if we have to tap materials like 316 stainless, it's going to be very problematic. And what we're going to lean on the most is the coatings that are on the machine tap that are going to give us the best choice or the best results to get proper tapping without breakage. If we can use uh, like emulsion, right? That 10 to 12% rule for something like 316 stainless steel would be where you want to be. If you could add, um, something like this fluid that I was showing you to the mix, even if you put this somewhere in the table of the machine and dip the tap and still ran the coolant, you're going to get the best results with this stuff in something like 316 stainless steel for
Okay.
sure.
All right. Well, this is the time for the webinar for us to take questions from the audience. And to begin with, we received some questions during the webinar registration process. And that's what the three here that you're looking at on your screen right now. So let's start with the first one there, Tom. What is the best choice of cutting tool or cutting fluid for tapping I can't read it. It's
Yeah, stainless
SS316.
steel 316, and that's the one that I thought you were referring to. I would tell you this fluid right here is a great, excellent choice. Having coolant, water soluble coolant, at least at 10% emulsion would be ideal. We have cutting taps that are coated with a PVD coating process we call GLT1, and that will greatly help with tap machine cutting taps for 316 stainless steel. And even in the case of cold forming, which is an option for 316 stainless steel, all the same things. Amugi fluid would be helpful. The 10%, 12% emulsion, and using again always with cold forming taps a coating. In the case of stainless steel, there's several choices, but I would even say our multi tap line with TICN is a great choice.
Yeah, just to clarify, the question I asked initially actually came in from one of the audience members live. They're doing a medical application and they're not allowed to run any fluid. So we're just kind of wondering what the best practices would be if you're in that situation. And you sort of covered that, but is there anything else you would add to
Well, that's when you might tap out for thread milling options. That's a whole nother discussion, but that is something that has led us to this thing. See, a Mugi, we make taps and thread mills. So we can address problems like that from all different sides. But I would tell you, um, taps, like we said, lubrication is really important. So maybe in the case of a medical dry application, the coating itself could be the only lubricant used. And that could be something we would still be able to be helpful, but tap life will suffer greatly without any kind of additive lubricant.
that? Okay. So let's do that second question. Can you explain the dynamics of rigid tapping without using any type of special holder?
So if I understand this question correctly, remember we had a slide where we showed the tapping cycle broken up into 7 distinct stages, and it's a unique cycle, the tapping cycle, right? And it happens in seconds. So today with a rigid tapping cycle, yes, your spindle has an encoder. I think there's over 200 trigger points, but it's not perfect, right? Every 3 degrees, there's a little bit of error. When I grind a tap, there's a tolerance on the pitch I grind. When I tap several holes in a piece of material like titanium, the tap is made out of powdered metal, cobalt vanadium steel. It grows. So if you do not have any compensation in your assembly, if you will, your tap is the compensating, it is the sponge, it is taking wear and tear It's changing direction. It's being beaten, if you will, in that automatic cycle. And the reason why we are so adamant about using soft synchro technology is we want to give your tap a break. We want the tap to last longer. We want it to make better threads, to operate at faster speeds. So if you're going to go into rigid tapping, if you're just going to use a generic collet chuck, your tap itself is the shock absorber. I hope
Okay.
that helps.
I hope so. Let's do our last question there. It's when thread forming, how do you determine the best tap drill size versus percentage of thread to achieve the best or best resulting thread form at the peak of the thread?
No, that's a good question. There is some like alchemy to cold forming threads. We are helpful at Amugi where, if you weren't aware, every Amugi cold forming tap um, has marked on its shank the suggested drill size for that tap. Um, Now, one of the things I say alchemy is all materials, flow differently when we cold form them in the tapping process. Some, more ductile materials, they form very easily. As we get into more difficult materials, they don't flow as easily. And it becomes, you're going to always have to think about that torque. So we give you a starting point, which I think 9 times out of 10 is going to get you the peak performance for not only the thread profile, but the tap itself. And we mark it in our books. We put it right beside the tap choice in our catalog. We mark it on the cold forming tap shank. And we're also, offering a lot more choices and drill sizes in our program because they're carbide taps. They're very precise. Um, they so you have a lot of increments you can move in. I think 50 micron increments a lot of times. So when it comes to cold forming, we give you a suggestion right off the bat that is helpful, and it's based on that 65 ish uh, percentage of full thread profile, which is plenty. And think of this in the metric system. There's actually a very smart allowance in the metric system for cold form threads, meaning a 6H cold form thread has a 7H um, tolerance allowance for the minor diameter that is formed by that tap. And we need to think about more of that in our unified thread series as well.
All right. I'm going to go back to this medical question because we had a follow up to what you suggested before, and it's a good point. If there is no coolant, could we talk a little bit about the performance of tap coatings and how would you advise someone if they're going to rely on the coating? What should they be looking for?
Well, one of the things I started our conversation, Dennis, about being a helpful hand. I'm sitting in Amugi Franken USA HQ, which is a technical center with machine tools, and one of the things we can do for such an instance, right, is we have a staff here that could process their work piece material in our lab here to try to work out a strategy, tooling, operating parameters that would make most sense for them to start with something where we have to have a dry situation for taps in a very and I would imagine a tougher material. So that's one way we can help.
Okay. So I don't know if we have any other questions from the audience, but I think we had someone specifically asking about I'm not sure if I'm reading this right. M3 6HX for grade 5. Is that titanium? I'm not sure if that's supposed to be titanium. Um, if we can get some clarification on that question, I'd be happy to go into it. Um,
So
oh,
M.
oh, I see. There is a side input for coolant on the speed synchro. Is that the only way for coolant through, or can the machine coolant through go direct through the tool instead of the side input?
So in our we have two different styles of speed synchro, and they're really based on the size range. The standard, we can put coolant through to the tap. Okay. Um, and then also the mini that you saw in the video, I believe we can still deliver coolant um, to the tap itself. So I don't. If we can get more information, if someone's really interested in that, we could follow up. Just knowing the machine model that they're working or looking at to put something like the speed synchro in, and we can best tell them what the coolant delivery would be.
Okay.
Okay. But yeah, they
So,
are marked IKZ. So IKZ in our system is internal coolant Z axis through the tool.
okay. All right. So, yeah, I should have advanced this slide, but if anyone is wondering if you didn't get a question answered, um, you can scan that QR code and you'll go to a page on the Amugi Franken website to get an answer for a specific question you might have related to this discussion. You can also click on the link if you want to download the PDF of this presentation. There's a link embedded in the PDF document on this slide where you can go and apparently there's a drill size pocket card that you can receive if you do that. So I thought I want to mention that. Um, if Are there any other questions that have come in from the audience? Tim, if you can just shoot me a message and let me know. Okay, so do you want to just pop up the questions so we can see it? All right, I see something here. It's what about the tap gullet variations versus strength? How many cycles before the tap metal fractures? I'm not sure if that's two different questions. Okay, I think that might be just about it, and we are running out of time. Anyone who does have questions, so please use these tools here to submit them after this event is over, and just again, someone from a movie will get back to you and answer your questions more fully. And if the questions that we've been asking here today, back and forth from the audience, if you don't feel like you got a full enough answer, we can always have them contact you directly. And you can, again, do that by scanning that QR code. Or if you want to get a hold of Tom directly, this is his contact information right here. Uh, and again, you can just download the PDF of the slideshow for both Tom's presentation and the slides that we've provided here. They're available in links at the on the HTML page on our website where this webinar is being broadcast. If you just scroll down, you'll see the links, and you can get them right from our page there. So with that, I want to thank Tom for your time and sharing all of your information with us, your expertise, your vast knowledge. Um, really appreciate that. I hope the audience found it informative, and let us know. Send us an email. Let us know if there's something else that you'd like us to cover in a future webinar. And speaking of future webinars, we invite you to register for our next one, which will be on June 26th. And it's going to touch on the article coming up in our May issue. No, June issue. I can't remember what month I am in. And it's going to address core competencies for the aerospace market. So we will look forward to seeing people there. And with that, unless there's something else you would like to add, Tom, I think we can close this
Thank
session
you,
out.
Dennis. I was my pleasure, and thank you for having me.
Oh, and no, it's my pleasure. And again, thanks. It was a great presentation, good information. Thank you.
Take care.
So long, everyone.